where we left off last time, we had talked about gyres. And gyres formed due to the fact that Coriolis effect was occurring. I put a video up about Coriolis effect. I'm going to put one up about Ekman Spiral and upwelling and downwelling too. So if you need a review of Coriolis, take a look at that. I know it's something you learned last year in physics. Another phenomenon we see in the ocean that is related to Coriolis effect is the Ekman Spiral. So in this picture, which is in your book, I think it's 7-6. It is in my book, but I know I have the oldest of the books. We have the wind. The wind is moving. It's the green arrow here. We can pretend it's blowing due north. And what happens is, through friction, some of the energy, you should know it's 2% of the energy, is transferred to the current, to the water surface, excuse me. But what also is happening is that that water begins to move. But due to the Coriolis effect, the water doesn't actually move in the same direction as the wind. It moves at a slightly offset angle. Right at the surface of the water, it's 45 degrees, right here. That would be 45 degrees right there. The purple being the surface of the water, the green being the wind. As that first layer of water begins to move, at the very bottom of that layer, there's water particles that are rubbing against other water particles and transferring more energy. Now notice, the size of the arrow indicates the energy involved in the movement. So the wind has the most, the surface layer has a little bit less, the layer below that in pink even less. So it's not moving as fast. It's also not moving in the same direction for the same reason. The Coriolis effect is also acting on it. And that continues as we move down the water column until we reach a depth usually around 100 meters, in which the water is actually moving in completely the opposite direction of the wind. And that's kind of a weird idea to think about. We can actually see this on our boat on a windy day. We put the, say, the CTD off the boat, and it's, being carried slightly in one direction. As you lower it, it can actually change direction. We obviously are not in 100-meter water, but you can see it goes about 45 to 90 degrees different from the wind surface, which is kind of neat to see. Overall, if you add together, and remember, arrows can indicate vectors, strength, remember? If you add together all of this energy of these flows, the transfer, so on and so forth, we have an overall net movement of water that is 45 degrees to the wind. And we call this Ekman transport. Same picture. And I think I said 45 in the last slide. It's 90 degrees. It's at a complete right angle. So we have the wind going this way. And the water as a mass overall is moving to the right. This is kind of an important idea to know. And obviously there are at least one person you should know who figured this out, Ekman. Ekman was a scientist from Norway, and he figured out and developed this model with information he got from Fridtjof Nansen. Fridtjof Nansen was the captain of a ship called the Fram, which we'll talk about a little bit later. Now, this diagram is for transport in the northern hemisphere. In the northern hemisphere, overall transport is 90 degrees to the right of the wind. In the southern hemisphere, because the Coriolis effect works in the other direction, the overall transport is still 90 degrees, but it's to the left of the wind. These two give rise to a phenomenon we call geostrophic flow, the Ekman transport and the Ekman spiral. Now, this picture is also in your book, and I'm going to talk about the bottom picture first. Basically, what we have happening is we have to imagine a gyre. So we'll pretend this is a gyre. We have a boundary current here, and here, and here, and here. And Coriolis effect is working on all of those. And so there is Ekman spirals coming off of these currents. And we know that there's this sort of general wind direction. You can see it in this diagram. I'll make them as, say, like a green color like they are here. Winds generally sort of go in this direction. What that means is, and I will draw this in red, is that when the wind blows, we have a net transport of water to the 90 degrees to the right of that wind. And that is continually acted upon. And what happens is you cause the water to begin to bend. Let me see if I can do this again. The water that was normally moving in these sort of like square boundary currents, kind of megasphere, the Ekman transport causes them to have these center-seeking slight transport of water. And what we end up with is a hill. We call this convergence. Anytime you have water piling up in an area, we call that convergence. So in the middle of these gyres, we have convergence, a pile of water, a hill. And they can be actually really large, like 6 feet in the center of the Pacific and the Atlantic gyres. Now, the same time Coriolis effect is causing the water to pile up, it's also causing it to be shifted, sloshed, slightly to the side of the gyre, which is why, if you look at this diagram, our center is not in the center. It's off to the right a little bit. This is because there's a sloshing effect. The Earth is rotating this way. And yeah, I'm sure you've like sloshed water around in glass. So the hill sloshes away from what would be true center towards that center. So the hill is off to one side more than the other. Now, anytime I don't know if you ever try to make a pile of water, it doesn't work out so hot. What's happened is, and up here on A, we're looking at a cross section. So it's as if they took B and sort of flipped it on its side. So let me clear this again. And we would have like the United States over here and Europe over here if we were looking at the Atlantic. And we would have this hill of water. Clearly, it's not to scale. What happens when you have a pile of water is that gravity acts on it, and the water should run based on gravity. I think gravity is red in this diagram. It should run downhill. And it sort of does. But we have water moving again, and what always acts on water moving? Coriolis effect. And the Coriolis effect, I know it's drawn in purple and it's pointing uphill, but basically it begins to shift that running water to the right again. So we ended up with, overall, when you put together these two forces, the water bends to the right as it moves down the hill. What effect does this actually have on currents? It causes something we call western intensification. Now, if we're looking at this diagram, let's switch back to B, and we're looking at it from above, the western boundary current is over here. As that water slides off of that hill, it's going to be fastest, because the hill is closest to the western side of the gyre. Notice it's spread out more on the eastern side as it comes down off of the hill. What this means is that the effect of this pileup, this convergence on western boundary currents is much more pronounced than it is on eastern boundary currents. That's why you have more water flowing. We end up with western boundary currents having different characteristics. Generally speaking, western boundary currents are fast, narrow, and deep. These three effects are due to western intensification. It's faster. It's sort of like if there's the difference between the top of the hill and the side of the ocean is greater, so the water flows faster. It's a bigger drop. Western boundary currents are also narrower. If you go back, I'll go back and look at the cross section again. There's a smaller distance. If you look in this picture right here, all of the movement of water is across a narrower area compared to the eastern boundary current. You have a lot less room for it, so it's a narrower current. It's also deeper. When you have more of that water flowing into a narrower area, it's going to take up more space. Now, one of the characteristics of western boundary currents that is not due to western intensification is that they're warm, and that's just because they come from the equator. So when we think about the fact that fast, narrow, and deep are caused by that convergence in the middle of gyres, a little offset, you can see why eastern boundary currents have the opposite effect. We'll go back to the picture once more. They are wider because they have more space. They have more space. They are slower because they have a much farther distance for the water to fall down. They go all the way this way instead of just down there. And they're narrower because the water gets to spread out across a larger surface area. In terms of coldness, they're colder, but that's not due to differences in western intensification. We will end here, and we will talk about currents and climate on the next video.